So, let's discuss about vector and scalar quantities. Starting from scalar quantities. In physics, a scalar quantity is any quantity that has only magnitude. Another word for magnitude is size, but no direction. So, anytime you come across any quantity in physics, and that quantity tells you only the size or magnitude of the measured parameter without making any reference at all to direction, that quantity is a scalar quantity. Example, you have temperature, for instance. Now, temperature only tells you the magnitude because temperature is the degree of hotness or coldness of a body. So temperature just tells you how hot or how cold a body is without, it can't even give you a direction because you can't say the body is 30 degrees Celsius in the north direction. It doesn't make sense. So it just gives you the size of the measurement without pointing to a specific direction. So we have other scalar quantities. We have mass, for instance. We also have distance. We also have energy, etc. So there are many of them. So all these quantities tell you only the size. On the other hand, vector quantities. So what are vector quantities? They are those quantities that have both magnitude or size. Another word for magnitude is size. And they also have a specified direction. So you see that vector quantities gives us more details. It doesn't just tell us the size of the measured parameter. It also tells us the direction it is taking. So from these two definitions, you already discover that the major difference between a vector quantity and a scalar quantity is just direction. Whereas vectors have direction, scalars, they don't have any direction. So it's now very important for us to note the directional properties and sign conventions of every vector quantity. So let's study that right away. Talking about the directional properties, you have the north, the east, the south, and the west direction. So these are the four possible directions a body can take. In between the north and east is the northeast direction, the southeast direction, the southwest, and the northwest. But basically, these are the four major directions a body can take. Now that is it for the directional properties. Now what about the sign conventions? This is the positive y-axis. This is the positive, that should be positive, not negative. This is the positive x. This is the negative y direction, and this is the negative x. So anybody that is going towards the north is going to take up the sign of positive because it's heading towards the positive y-axis. Anybody heading towards the east will be positive. Towards the south will be negative because that's the negative y. And then towards the west will also be negative. So you see that from what we have here, scalar quantities can only be positive. It can only have a positive value because it does not make reference to direction. So it's always positive. Apart from some cases like maybe temperature, where you can have negative 32 degrees Celsius, for instance. When water is freezing, the temperature begins to go lower and lower till it gets to the a negative value. But most often than not, it's always a positive value for scalars. But vectors can have, positive or negative value. And this is because of its specified direction. So if a body is going towards the north, it's going to be positive. If it's going towards the south, then it's going to be negative. So that's why a vector quantity can have either a positive or a negative value. Okay, let's talk about addition of vectors. How do we add vectors? So, addition of vectors. Now, talking about scalar quantities, we just add scalar quantities using the normal addition method. But vector quantities, can't just be done that way because it makes reference to direction. So the signs are going to come into play. But first of all, whenever we add vector quantities, our answer is what we call resultant vector. You need to note that when we add vector quantities, our answer is what we call resultant vector. And just to explain this, I will explain that and then I'll tell you what the resultant vector is. Let me just do this with currency. From the part of the world I'm making this video, the currency we use is Naira. So let's say that two students one has 2 Naira, and then this is student A, for instance, and then student B has, say, 3 Naira. Now these two students decides to put their money together, that's adding it together. Say they wanted to get a drink which is 5 Naira, so the drink is 5 Naira. So student A decides to bring his 2 Naira and student B decides to bring his 3 Naira. Now you see that if they add it together, they are going to be able to purchase the drink which is 5 Naira. Now what of the case where we have another student, say student C, and student C has 5 Naira all by himself? Now you see that, let me specify this drink. Now you see that student C can also purchase the drink of 5 Naira without any help whatsoever. So we can say that the amount of money student C has is the resultant of the amount of money student A and student B have all together. So you see that only student C can purchase the same thing student A and B can purchase. So that's what I mean by resultant. So a resultant vector is that one single vector, in this case student C, that will have the same effects in magnitude, that means in size, and also in direction as other vectors acting in a system. It doesn't only have to be 2 vectors. Another illustration can be, say student A has 3 Naira, student B has 4 Naira, and then say student C has 3 Naira as well. So this is student A, B, and C. Now if you add the amount of money they have together, it's going to give you 10 Naira. And if we have another student D, that has all by himself 10 Naira, he is also the resultant of these 3 students. So it could be 2, 3, as the case may be. But just one single vector, in this case I'm using money as an illustration, that will have the same effect as many other vectors acting in a system. That one single vector is referred to as a resultant vector. So for addition of vectors, I'm just going to show you how to add vectors with a simple illustration. So if we have, say, a block of wood, and then let's say we have a young boy pushing against this block of wood with the force of, let me make space there because I want 2 boys to push against the block of wood for this illustration. So we have a boy pushing with a force of 5 Newton, and then I have another boy, they have the same strength, and they're pushing, and he's also pushing with a force of 5 Newton. Now how do we get the resultant vector? Because of vectors make reference to specific direction. So, and I talked of the directional properties and sign convention of vectors earlier, so I'm just going to illustrate one more time. This is the north, this is the east, this is the south, and this is the west. So you need to know that vectors are represented by a straight line with an arrowhead, and the direction of the arrowhead, or where the arrowhead is pointing towards, tells us the direction. So you see this 5 Newton force pointing towards this direction, which is the east direction. That means they are pushing the block of wood to the east. And so you need to know that about vectors. If it's pushing towards the north, the arrowhead will be drawn in this direction. So just know that. And from the sign conventions, this is the positive side, this is the positive x, negative y, and then negative x. So since these boys are pushing towards the east, the value or the value here of the magnitude is going to be positive, because that's the sign of the east direction there. So we just add it by saying the resultant will be equal to 5 plus 5, because positive 5 plus positive 5, they are heading towards the east, and then the resultant is going to be 10 Newton. So that's the single force that will have the same effect as these two forces pushing against this block. So if we wanted to represent that diagrammatically, we are going to draw something like this, and then the block of wood. You also need to note that the magnitude of the vector is proportional to the length of the line drawn. So now I want to represent a force of 10 Newton. The line is going to be double of the one of 5 Newton we have here. So what if we have another scenario like this, the same block of wood, and then we have a boy pushing, only him, a force of 10 Newton, and then we have another boy pushing from the opposite direction with a force of 5 Newton. What will be the resultant? The resultant will be, using the sign conventions, this 10 Newton is pushing towards the east, so it's positive 10, so 10 plus. Now 5 Newton is going towards the west, which is this direction, and that's a negative value there, so that is going to be negative 5 Newton. Plus minus will give us minus. 10 minus 5 will be the resultant, and then the resultant is equal to 10 minus 5 is 5 Newton. Can you see that now? And you need to note that the resultant will take the direction of the greater force, or the greater displacement, or the greater acceleration. Any vector that is under consideration in this case is force. So if I wanted to represent this diagrammatically, the representation will be in this form: 5 Newton and then the block of wood. You see, the direction is towards the east because the greater force in this arrangement is this 10 Newton. So is 5 Newton from the 10 Newton will cancel this 5 Newton pushing against it, and the bus will still go in the direction of towards the east with a force of 5 Newton. So that's how to get the resultant vector. So generally, if you want to get the resultant vector, if the vector are in the same direction, like in this case, we have 5 Newton and 5 Newton in the same direction, you just simply add. But if the vector are in opposite direction, like the case we have here, you are going to subtract. There are two ways you can represent the resultant vector. One is by sign convention, that's with respect to the direction, or the sign of the direction, and one is the directional property. So let me just explain that. So I'll use another illustration. Say the same boy with a force of 5 Newton is pushing against a block, and in this case we now have another boy of 10 Newton, with 10 Newton rather, pushing with a force of 10 Newton. So I just want to duplicate that. So we have the same case scenario, and we asked to get the resultants. So you can use any of these methods to get the resultants. You don't have to use the both of them, in a particular question. Just showing you. Now, using the sign convention, we're going to get the resultants with respect to the signs. Now, 5 Newton is going towards the east, pushing against this block of wood towards the east, and we know that the eastern direction has the sign of positive, so that's positive 5 Newton, and we add the other one. And then this one is pushing against the block, and it's pushing towards the direction of the west. You see the direction pointing towards the west, and we know that the sign associated with the west is negative, so the 10 will be negative 10 Newton. Plus minus will give us minus, so the resultant is equal to 5 minus 10 Newton, and then the resultant will give us negative 5 Newton. So the negative sign we have there tells us the direction of motion, and we know that the west direction is associated with the negative sign, so this negative sign tells us that the resultant vector has the direction that is going towards the west. What of the directional properties? Now for the directional properties, we just use the addition method I taught you already for resultant vector, that if they are in opposite direction you have to subtract, and if they're in the same direction you just have to add. So they're in opposite direction, so we're going to subtract. So we have 10 Newton minus 5 Newton, and then the resultant is 5 Newton. And I told you that the direction will be in the direction of the resultant will be in the direction of the greater vector, in this case force. So 5 Newton, and I'm going to represent the direction like this. So this way or this way, you have the resultant vector. The 5 Newton there is the magnitude, while this arrow pointing towards the direction is the direction for this, and then the negative sign here is the direction. So that's how to get a resultant vector. Alright, in some cases we can have vectors arranged in this form, where we have a couple of vectors acting on a particular body in the same direction. So if we consider this case, we have three individual vectors acting in a certain direction. That's if we consider this side, all these vectors are acting on this body in the eastern direction, right? And then the other way around, these vectors are acting towards the west. So if we have this kind of problem, we can still find the resultant, and the way of getting the resultant, first of all, using the directional properties, we just resolve, or rather, let me not use the word resolve. We just try to add up all the vectors that are in the same direction, on both sides. So these ones moving towards the east, we can just add them up, because remember, if vectors are in the same direction, you're going to add. So we just add up all these vectors to make it one vector, to get the resultant. So it's going to give us the resultant for just these vectors acting towards the east is 5 plus 3 plus 7, and that should give us 15 Newton, right? 15 Newton in this direction. We're going to redraw, and then the resultant for this problem, that should give you R. The resultant R should be equal to, we're going to add everything there. 10 plus 5 is 15, plus 2 we have 17 Newton, right? Now if we redraw that, so I'm just going to move that down a little bit. So if we're going to redraw this is the body they were acting on. Regardless of the size, let's say that it's still the same mass, nothing changed, then this 15 Newton, we just have to make it longer, because the magnitude of the vector is proportional to the length of the straight line drawn. So this will represent the 15 Newton, and then over here we have a longer one representing 17 Newton. So you see, we have added all those vectors into single vectors, and then we can finally get the overall resultant by subtracting, because since they're opposite direction, you just have to subtract 17 minus 15, and that's 2 Newton. And to represent this diagrammatically, as we've been doing before, is going to be, this is the body they were acting upon, right? So remember, the direction will be that of the greater vector, in this case force. So this will go 2 Newton in the west direction. So that's literally how to do it. Alright, when we talk about the sign convention, so I'm just going to try to bring this down a little bit. So using the sign convention, the resultants, we just have to add everything, noting their sign. So for all these bodies, all these bodies are moving towards the east, so their sign is going to be positive eventually. So we just add everything up, or okay, let me just leave it that way, then plus, and then let's now add or subtract these ones based on their sign convention. They are moving towards the west, so they're going to have negative signs, all of them. So this is minus 10, minus 5, and then minus 2. So all of this should give us 15 plus. All of this should give us negative 17. Minus 10 minus 5 is minus 15, and then minus 17. So plus minus, find out the resultant is 15. The plus minus there should give us minus, right? And then we have 17. And 15 minus 17 is negative 2. So the negative value we got there is telling us the direction of the resultant, that's towards the west. So anytime you have multiple vectors, you can just get the resultant by doing it this way. Using the sign, rather the directional properties, you're going to add all the vectors that are towards the same direction. So just resolve it into one single vector on both sides, and then either add or subtract depending on whether they're the same direction or opposite direction. Or you can just use the sign convention and you get your answer. So that's practically very easy. So you just need to know that resultant vector, I like to see a resultant vector as kind of a proud vector, trying to say that even though other vectors they can be 2 vectors, 3 vectors, the resultant vector is just trying to say that what all of them can do, only him can do by himself. So that's what the resultant is all about. So all these forces acting on this body, only a force of 2 Newton will have the same effect in magnitude and direction. So resultant vector is that one single vector that will have the same effect as other vectors acting in a system. So that's just it.